Okay, Assalamualaikum and very good morning to all the participants. Welcome to our series of webinar under IEEE PES Malaysia. Today we are going to discuss the topic on the stability analysis of DC microgrid integrating wind, fuel cell and microturbine power generations system fed to multi-machine systems from our honorable speaker, Professor WANG. Before we start to the webinar, I would like to share some regarding the activity or IEEE PES. Okay, please allow me a few minutes to share about the PES. Okay, IEEE Power Generation Society, who we are and where we are going. So IEEE Strategic Plan 2020-2025, our missions, we foster technological innovations, excellence for the benefit of humanity. For our visions, we will essential to the global technical community and to technical professionals everywhere and be universally recognized by the contribution of technology and of technical professionals in improving global conditions. We have embraced 6 core values, which is trust, growth, nurturing, partnership, service to humanity, integrity in actions, and global community building. As a society, IEEE will drive global innovation through broad collaborations and the sharing of knowledge, enhance public understanding of engineering and technology, and pursue standards for their practical applications. Be trusted source of educational services and resources to support lifelong learning, provides opportunities for career, professional development, inspire a worldwide audience by building communities that advance technical interests, inform public policy, and expand knowledge for the benefit of humanity. IEEE, as a world's largest professional associations, advancing technology for humanity. And in terms of global reach, IEEE have more than 400,000 members within the reach of more than 160 countries. And we have more than 120,000 students member, and IEEE have conducted almost 2,000 annual conferences. In terms of technical breadth, we have about more than 4.5 million technical documents, and 2,000 plus top-cited protocols, and more than 103,000 active standards, and we do have published 49 technical societies. In terms of engagements, IEEE do the public policy engagements, global humanitarian efforts, education and certification, as well as ethics in technology. PES is the second largest technical society in IEEE. Out of 37 or 37 other technical societies under IEEE. And IEEE Power and Energy Society membership can help you to grow and maintain your technical expertise, get connected to other professionals, contribute to the future of power and energy, save energy on valuable programs and materials, and stay technically proficient with the PES via online webinar tutorials, on-site training workshops, practice-oriented technical journals, and also plain talk basic courses for industry novice. And PES is deploying very significant resources for training and lifelong learning activities for those who are participating our activities. And of course, we do have many resources for CEUs and PDH. For the resource center, the IEEE PES cover about 1,400 items, the most extensive library of content in world devoted, which is exclusively in the field of power and energy. So everything, every document putting in one place, such as tutorials, videos, technical reports, journal articles, archive webinars, conference slides, and many more. For the global engagement through the local chapter, we have Region 1 to 7, which consists of 121 chapters and almost 20,000 members. And Region 10 is 36 chapters with 33,564 members. Region 8 consists of 48 chapters for 500 and 715 members. And Region 10, which is 45 members, covers more than 10,000 members. So here are the lineup of the IEEE PES Malaysia leadership, which established on 1994. And now our chair is Prof. Azri Mukhlis. And what we did as a society, we conduct the invited lectures, conferences, award for outstanding engineers, collaborating and linking with industries, technical activities, final year project awards, reaching out to members and senior member drive. And if for those who are not becoming a member, please join us as a member and have a benefit and privilege by becoming our members. So we do have free members PES student membership for 1 year only, where the students are able to enjoy a free subscription to PES award-winning Power Engineering magazine, gain free access to PES Resource Center with hundreds of technical reports, tutorials, video, as well as presentations, and receive free membership in your local PES chapter, receive discounts at dozens of PES-sponsored and co-sponsored conferences and meetings in your area around the world, and take the advantage discounts for technical tutorials and utilize PES Careers, which is a free service designed to specifically help undergrad as well as the graduate engineering students connect with the employers in the entire world, focusing on the power and energy industry. The offer is only valid for individuals for 1 year only, and those who have never been a PES member. Join me and as we bring more power to the future. This is the contact email for the PES Malaysia, and please join us at this under the website as well as the Facebooks. Here the picture of our EXCOM for 2021. Now before we start the presentation session given by the Prof. Lee Wang, let me introduce a little bit about Prof. Lee. Prof. Lee?
Yes.
I try to find your biography. Wait a minute, Prof.
It's okay.
Prof. Lee Wang received his PhD degree from the Department of Electrical Engineering, National Taiwan Universities, Taipei City, Taiwan in June 1988. And since August 1995, he has been promoted to be a professor at the Department of Electrical Engineering, National Cheng Kung Universities, Tainan City at Taiwan. He was a visiting scholar of School of Electrical Engineering and Computer Science, Purdue University, West Lafayette, USA, from February 2000 to July 2000, and School to Electrical Engineering and Computer Science, Washington State University, Palmans, Washington, USA, from August 2003 to January 2004. He was a research scholar of Energy System Research Center at University of Texas at Arlington, Texas, USA, from August 2008 to January 2009. And currently, he has been appointed as external assessor for Department of Electrical Engineering, Faculty of Engineering, University Malaya, Kuala Lumpur, Malaysia. His current research interests include power system dynamics, power system stability, AC machine analysis, as well as renewable energy. Prof, without further delay, the screen is yours. Over to you, Prof.
Thank you. Hi, good morning, everyone. I'd like to thank Chairman to introduce me. And the title of this talk is Stability Analysis of a DC Microgrid Integrating Wind, Fuel Cell, and the Microturbine Power Generating Systems, Phase 2 Multi-Machine Systems. My name is Li Wang with the Department of Electrical Engineering, National Cheng Kung University, Tainan, Taiwan. The outline of today's talk includes following: abstract, system configuration and mathematical models, economic analysis, small signal stability analysis, dynamic and transient analysis, conclusions. Okay, the first part is about abstract. This talk discusses both stability and economic analysis of DC microgrid (MG), composed of different renewable energy power generating systems (REPGS) and the various energy storage systems (ES, SS), Phase 2 kilowatt and the megawatt multi-machine systems. The studied DC microgrid is composed of a wind generator, a fuel cell, a microturbine generator, a vanadium redox flow battery (VRFB), a supercapacitor, a bidirectional DC-DC converter, and a bidirectional DC-AC inverter. The energy storage system based on supercapacitor bank and the VRB is connected to the DC microgrid through the bidirectional DC-DC converters, while the multi-machine power system is connected to the DC microgrid through a bidirectional DC-AC inverter. The feasibility of the study DC microgrid is evaluated by using economic analysis, while the mathematical model of the study DC microgrid with the renewable energy power generating system integrated with the energy storage system are established. The steady state, dynamic, and the transient responses of the study DC microgrid Phase 2 multi-machine system under different operating conditions are performed to evaluate the smoothness and the stability of the studied DC microgrid. Now the following are the keywords: DC microgrid, wind farm, fuel cell, microturbine, hybrid energy storage system, vanadium redox flow battery, supercapacitor, multi-machine power system, economic analysis, and stability. So from this figure, you can see this is the discharge time and rate power, and this is the system power rating. You can find the flow battery is about, the power rating is about 20 kilowatt to 50 megawatt, and the discharge time and rate power is in hour. You can see the high power capacitor here is the power rating is about 20 kilowatt to 1 megawatt, and the power rating, the discharge time and rate power is about in second. So these are two different kind of energy storage, but we want to connect it together to constitute hybrid energy storage system. On the other hand, we can find this is power density versus energy density. You can find a supercapacitor here have a high power density but low energy density. But VRB here have a high energy density but low power densities. So we can try to combine two different power density and the energy density together to constitute a hybrid energy storage system. So next, I will show you system configuration and the mathematical models. In this part, I will show you system configuration, model wind power generating system, model solid oxide fuel cell (SOC), model microturbine (MT), model hybrid energy storage system (HESS), model DC to AC voltage source inverter, and the model of multi-machine power system. So the first part I show you system configuration. This is the system configuration 1. You can see we have a SOC here, PMG wind turbine here, and the PMG for the microturbine here. All this power generating system will through the individual voltage converter connected to the DC link of 1200 volt. And the DC link here will connect it to the DC load through the buck converter, D to D buck converter. And remember, we have two different kind of the energy storage here. This green one is the about the supercapacitor, but here is a bidirectional DD converter, and this purple one is a VRB. Then here is the bidirectional D2 converter. So with these two different kinds of hybrid energy storage system, we will connect it to the this link. Then when the input power is fluctuated, these two different kinds of energy storage system want to compensate the power fluctuation. So this is the first one, system configuration. The system configuration 2 is connected the previous system configuration 1 to the multi-machine system. You can find this is a simplified Taiwan power system. And here, this link will through the inverter, step transformer, transmission line, then connect it to the bus of the multi-machine power system. So we want to connect it the DC microgrid, then connect it to the multi-machine system through the inverter, step transformer, and the transmission line. So in this talk, we have two different kinds of system configurations. Now, next step, I'll show you model of wind power generation system. This is a very simple model. We can see the wind applied to the blade, then rotated to drive the shaft of the PMSG. The output three-phase is connected to the DC link of 1200 volt through the voltage source converter. So when the wind speed is between the cut-in wind speed and the rated wind speed, for example, cut-in is 4 meters per second, rated is 20 meters per second. Between this way, then the output mechanical power is a cubic of the wind speed. And when the wind speed is input, then we want to know how to control output power. If the wind speed higher than the rated wind speed, then the pitch control system must be activated. If the wind speed is lower than the rated wind speed, then this control block diagram will not be activated. So you can see we feedback the reference power with the active power through the PI controller, then get the reference for the pitch angle. Then the pitch angle through the pitch servo, then we can get the actual pitch angle of the pitch angle control system. So this pitch angle is control the blade angle here. So when the wind speed is too high, higher than the rated wind speed, then this one will be activated. But the wind speed is lower than the rated wind speed, then this control block diagram cannot be operated. So we want to combine the wind turbine, generator, converter, and the pitch control system together. Then this will be the model for the wind power generation system. What about the PMSG? You can see this is the DXS QS DQ equilibrium circuit model for the wind PMSG. So we can use the DQX model to establish the mathematical model for our wind generator. Okay, next step, I'll show you about the model of the solid oxide fuel cell. Because solid oxide fuel cell is a high power, maybe connected to our high power system. So you can see this is a control block diagram for our system. I'm sorry, this one cannot be shown because actually it has a symbol here. But you can find, in this model, we fix the fuel utilization, UF. Utilization is a ratio of the reaction fuel flow to the input fuel flow. So you can find when the current, DC current here with the input fuel flow, then through the control block diagram, we can have output of the DC output here. So this control block diagram is used for our control of the solid oxide fuel cell. But remember, here's the DC output. If we control this one to the DC link, then the DC to DC converter must be used. Okay, next up, I'll show you the model microturbine. This is for the control block diagram for the high-speed one-shaft model, about 50 to 120 kiloradian per second. So you can find here is the input fuel flow rate. Here is the input air flow rate. Then the output the flow rate will be here in the burning room. Then the microturbine output flow rate will be here. Finally, we have the output mechanical power here, then transfer to be a mechanical torque. So this model will be used for our microturbine. But remember, this just hold of microturbine. If we want to have a power generation, then the PMSG, the generator, will be connected to here. Then the output power will be electricity. So next step, I'll show you model hybrid energy storage system, HESS. The first step I'll show you, the very important one is the vanadium redox flow battery, VRFB or VRB. You can see this is the parasitic losses using the dependent current source and the resistance. And here the two resistance represent the internal losses. So this is a very important equivalent circuit model we will use to represent the VRB. How about the supercapacitor? You can see we have the capacitance here and the two resistance to represent the over losses and the self-discharge phenomenon. So this model will be used for our supercapacitor bank. With the VRB here and our supercapacitor here, these two energy storage systems will through the bidirectional DC to DC converter. Our energy storage system will be connected here, but here we will have the 1200 DC link. So you can see when the energy is from this way, then it's the boost mode. The energy storage system will be discharge energy to the DC link. But when the energy is from this way, it means our energy storage system will be charged. So 1200 volt here will be charged your energy storage system. So we use the dynamic average model here to represent operation of bidirectional DC to DC converter. So this converter is very important because our control will be focused on the duty ratio of these two power switches. For the model of the DC to AC voltage source inverter, you can see the DC link 1200 volt here will be connected to the AC bus. Then we need to the DC to AC inverter, transmission line, step transformer, and transmission line to the peripheral bus. So how do we control this one? We need the DC link voltage as a feedback to control output D-axis and the Q-axis voltage. So this control block diagram will be used to control our VSI here. And finally, I'll show you the model multi-machine power system. So this is the one-line diagram for the simplified Taiwan power system. For example, here has a nuclear number 2, and our Xiehe nuclear large power, and our Zhonghuo single generator and the Xingda single generator. So we simplify Taiwan power system to be a 4 large synchronous generator. Through the generator, we have a self-transformer, transmission line, and the bus and the load. So how do we model the synchronous generator? You can see 1, 2, 3, 4. This is a very important 2-axis model for our synchronous generator. We can have the input current, input voltage, and the current here. Then the output will be the D-axis and the Q-axis voltage. Then the output will be the rotating speed and the torque angle. So this model will be used for our synchronous generator for the multi-machine system. Remember, in the multi-machine power system, we cannot use the detailed model. So this 2-axis model is a simpler model that can be used as a synchronous generator for the multi-machine power system. So each generator needs an exciting system. So IEEE Taiwan exciting model will be used for each generator. And the speed governor system will be used one for each generator. And our steam turbine and the control block diagram will here. You can see the valve in position here, steam input, to control the steam input through the steam chest, then through the reheater, through the crossover, then through the high pressure turbine here, intermediate pressure turbine here, and the low pressure turbine here. Then we combine the 3 different kinds of the turbine torque together to cancel the input torque for the synchronous generator. So this control block diagram will be used for each generator. So each generator has its own D and the Q axis quantity. For example, the voltage and current. So we have to convert all the individual D and Q axis to be a common D and Q axis. For example, each generator has a D and the Q axis quantity. Then we need to convert all this individual one to be a common D and the Q axis. So this is very important for our multi-machine study. We cannot use the individual one, but we have to use the common DQ axis to represent the multi-machine power system. So next step, I will show you how to perform economic analysis. There are 5 economic analysis methods. For example, the first one is cost energy, the equation here. Second one is simple payback time, SP, equation here. Discounted cash flow, DCF, equation here. And the benefit cost ratio, B over C ratio, equation here. And our net present value, NPV here. So in our study, I will show you the software RET Screen Expert. This software is used to evaluate the study system configuration 1, the DC microgrid only. So you can see this is a web page for the RET Screen Expert. Expert is developed by Canada and is a clean energy management software platform enabled for low carbon planning, implementation, monitoring, and reporting. So remember, in our I will discuss about this one, how to perform the configuration 1 for the economic analysis. And RET Expert is an advanced premium version of the software is available in viewer mode, completely free of charge. So everyone can use this one to study your country, your location, to study about the economic analysis. Now I will show you the different about the 4 different cases: case 1, case 2, and case 3, and case 4. Case 1 is configuration 1 without any throw system. Case 2, configuration 1 with SC only, with supercapacitor band only. Case 3 is the configuration 1 with VRFB only. And the case 4 have the hybrid SC and the VRFB together. So we need to compare different economic analysis, the index. The first one is about the pre-tax internal rate of the return, IRR, and the return on investment, ROI. You can find different value here. Next one is after tax, the IRR and the ROI have different values. And the benefit cost ratio, B over C ratio, have different values. And the simple payback time in year have different values. And the net present value, NPV, is per year for new Taiwan dollars here. So you can find the different cases have different value. So I want to compare which one is best for ours. But remember, the system have the supercapacitor bank and the VRFB have the very expensive. But even expensive, each one compared to the previous one, you can see you can accept this one because the each year have the NTD per year and the different years and different values can accept this one because even this is to hybrid. But I think it's in the future, fast one and the slow one can be combined together to constitute a hybrid energy system. Next one, I will show you the time of positive cash flow. For example, case 1, system without any energy system. You can see that when the cash flow is positive, it requires 8.6 years. And in 20 years, the net earn is about 6. Oh, I don't count it. It's this value. For case 2 system with supercapacitor only, you can find the positive cash flow time is 10.5 years, and we have earned money here. Case 3 is system with VRFB only. You can find the time of positive cash flow requires 12 years, and we can earn such money here. And finally, case 4 with both SC and VRFB is a hybrid energy system. You can see it requires 13.1 years, and the earn money is here. So when each one you can compare the years, compare the money. So in this talk, I will show you we use the RET Screen Expert software to compare the different cases. The number 4 case is very important because we use the hybrid supercapacitor and the VRFB together. And the other one maybe VRFB only, and the previous one will maybe SC only and without ESS. But this one with both hybrid energy storage system, SC can compensate the high speed response, and VRFB can compensate the low speed response. So when both one are combined together, then I think this will be used in the future. Next step, I will show you the small signal stability analysis. So when the system configuration is established, remember we have to choose the nominal operating point. So for the system configuration, we choose fuel utilization of microturbine fixed at 0.85 mole per second. Fuel flow rate of the fuel cell is fixed at 0.9 mole per second, and the wind speed will increase from 4 meters per second to 15 meters per second. So we keep these two flow fixed, but the wind speed change. So let's take a look about our eigenvalue or the rule of size. You can find if all eigenvalue, I will not show all eigenvalue, but I will show the dominant eigenvalue of the system. For example, wind farm mode is lambda 1 and 2. You can find when wind speed increased, it's this way and then return back. So originally, and the low wind speed have a better damping. But when high wind speed is become this way, the damping will get low. For the DC load model is lambda 19 and 20. You can find all the mode this way. When wind speed increased, then this mode will have a better damping. But for the VRFB mode and the SC mode, you can find all these two energy source systems will approach this way. Means the damping will be discrete. But even the damping is discrete, you can see their real part is very, very large, meaning they are very stable. So even we try to change the wind speed of the wind generator, we can still have a very stable operation for our solar system configuration 1. What about configuration 2? Configuration 2 have the DC microgrid here connected to our multi-machine system through the inverter, through the step transformer and transmission line. You can find we also keep the fuel utilization of microturbine fixed at 0.85 mole per second. Fuel flow rate of a fuel cell fixed at 0.9 mole per second. And wind speed also increased from the 4 meters per second to 15 meters per second. When the wind speed change, then all operating conditions will be changed. So let's take a look what happened to their eigenvalues. Because the multi-machine system connected with the DC microgrid, all the eigenvalues change. For you can say wind farm change to be more than lambda 25 to 26. You can see the more is also this way. When wind speed increased, it goes this way and then return this way. Very similar to the DC microgrid result. And the DC link mode, you can see the lambda 21 and the 22 all this way because the damping is increased. But what about the inverter mode? Because we have inverter just between the DC microgrid and the multi-machine system. You can find the lambda 23 and 24. It's this way. Means the damping is decreased. But the VRFB mode and the SC mode, you can see, just like the previous one, they are turned through the right way because the damping is decreased, but the eigenvalue still maintains stable. So when the wind speed is increased, you can see all the eigenvalue, the down eigenvalue, can maintain stable. So we use the model to understand if the wind speed change, then stability can be maintained. So this is our study about small signal stability. What about dynamic and transient analysis? We have divided two different cases. For example, dynamic analysis, we want to study about the wind speed changes. Case 1, responses of system configuration 1 and 2, when the wind speed of the hybrid renewable energy power generation system is varied. Okay, the speed change. So let's take a look at this one. We keep this one fixed, the fuel rate fixed, keep the fuel flow rate fixed, but the wind here we apply to an actual wind speed. This actual wind speed we can capture from some measurement from the wind tower. We can capture the wind speed. When applied to the blade, then all the quantity will have variation. Because remember, the wind speed may be very low to the 5 meters per second. The highest one may be about 18 meters per second. So with this wind speed applied, then all the quantity will be varied. So let's take a look. When the wind speed applied, then here you can find the output power is dropped down. But this output power still keep constant. because their fuel flow rate is keep constant. But input wind speed is changed, then the output power will be dropped down and then increased. What about the other one? You can find the DC link voltage. When the wind speed will changed, you can find the DC link voltage can keep nearly around 1.0 per unit value. Even have a large variation, but the variation is very small. And then you can find here the output of the converter. Because here the initially drop down increase, so output it had a similar result. Then the DC load voltage, the power here, due to the DC link voltage variation, then the power here is also variation. But you can see this one has a very small variation. Even it's a large variation, but small one. But you can see we have compared the hybrid energy system. It's a red one. And without HGSS, has larger variation. So we can find that when a hybrid energy system is included, we can keep the voltage here nearly constant at 1.0 per unit. And the power for the DC load also keep at a constant value. So this is very important. If without the energy system, large variation will happen. But when hybrid energy system is included, then the DC link voltage and the DC load power can be kept nearly constant. So very, very important performance for our hybrid energy storage system. What about the system communication tool? If we apply the same wind speed to here and this fuel flow keep constant, then you can find the output power is also have a similar drop down initially, then increased. But output power for SOC and the microturbine also keep constant. This is for the system communication tool. Remember, the DC link is connected to the multimachine system through inverter and the step transformer. So what about the DC load here? Again, you can see when the hybrid energy system included, then the power is keep constant, near constant. But without energy system, large variation still happen. And then you can see the output power here drop down, and the hybrid energy system power have a variation. You can find the power is initially drop down, increase, but the power here initially increase and drop down. So these two figures simply compensate to each other. It means our hybrid energy system has ability to compensate the variation or the power for the wind here. And even our DC link voltage can also be controlled very constant here. You can see the red one. Without any slow system, large variation also can be seen. Finally, I will show you the other one. How about the multi-machine system? Because the G3 is very close to the PCC, so you can find the red one is with the hybrid energy system. The black one is without energy system. When the system with energy system here, you can find it's very smooth. Make sure the active power here can be compensated. What about reactive power? You can find the red one is with HGSS. The black one is without HGSS. The reactive power can also be compensated. So you can find that we put our hybrid energy system here, but our generator here, the active power and reactive power can also be compensated by our hybrid energy system. So it's very important for our study. Our next one, I will show you another comparison. If our HESS, the capacity is changed, what happened to our system? You can find for the configuration 1, if a hybrid energy system with a capacity of 35 kilowatt, the peak value here will be 0.2 per unit. If we increase to be 50 kilowatt, you can find the peak value here will be 0.4 per unit. If our energy capacity is increased to 75 kilowatt, then the peak value will nearly to 0.6 per unit. It means when we change the capacity of hybrid energy system for the system configuration 1, their compensation output power will be changed. Then they also have the ability to compensate for the wind speed variation. So this slide shows you about the different value for our high capacity for the hybrid energy system. Now, what about transient analysis? Sudden trip of a wind farm. This is the case 3. Case 3 will show you when our wind farm is suddenly tripped at the time equal 10 seconds for the system configure 1 and system configure 2. For the system configure 1, you can find the input fuel flow is constant and the input wind is all keep constant. But when at the time 10 seconds, the power suddenly drop down to 0. But the other one, the other power here will be affected because their converter are connected to the same DC link. So when this one is suddenly tripped, loss of the load, loss of the power, then the other two power generation also have been affected. This is the first slide about the sudden trip of the wind farm. When the sudden trip wind farm happened, what about the DC link? You can find this a comparison about with a hybrid energy and with hybrid. You can find with a hybrid, then the value will be keep constant. Without hybrid, large variation happened. But at the supercapacitor here, when the suddenly triple the wind farm, their output power is positive to compensate the loss of the power from the wind farm. What about the VRB? The VRB also output active power to compensate the loss of the wind farm. But you can find different energy source system have different compensation. This one is up and down and the ramp down, but this one is up and then keep constant. So different control system will affect our output power of the supercapacitor and the VRB. What about DC load, the power? You can find when you compare the hybrid system and without hybrid system, the DC power here also can be keep constant with the hybrid. But without hybrid, large variation can also be happened. So this is for the system configure 1 under sudden trip of the wind farm. What about system configure 2? Again, here has the sudden trip of the wind farm. You can find originally the power here then drop down to 0. But the other two active power is also affected by this sudden trip because their converter are connected to the same DC link. Sudden happen, you can find the trip spike will happen at 10 seconds. What about the DC link voltage? Again, we compare the system with the hybrid energy system and without hybrid system, and the DC load with the hybrid and without hybrid. But this one I cannot clearly tell. But you can see if we have a hybrid, the larger variation will be compensated by the hybrid system. And how about the combined active power here? You can see when we have a hybrid energy system here, when the sudden trip of the wind farm, then output power will be suddenly increased and then gradually drop down to compensate the variation of active power, loss of active power. Finally, I will show you the generator, the number 3 synchronous generator here. There's two different figures. Red one is with the hybrid system. The black one is without hybrid system. Because the hybrid system is maybe through the inverter to connect here. So you can find when a sudden trip happened, they drop down and then gradually return back. But without the hybrid, they quickly return back. So this one is very different about the hybrid system. This is for the reactive power. You can see when hybrid system, when wind farm is sudden trip, oscillation can happen, but it can quickly stable. But this one has a large variation, then return back to the steady value. So according to this figure, you can find even the hybrid system is far from our synchronous generator. They still have ability to quickly make the variation or active power, reactive power to the steady value. But these two, maybe we need to design suitable controller to control their output power and make sure response can be quickly return back to our steady values. Numbers, there are case 4, transient analysis, when we change the capacity of the supercapacitor NO, the VRB. So case 4, SC has two different values, 9 kilowatt and 19 kilowatt. VRB has two different values, 26 kilowatt and 26 kilowatt for system configure 1. And the wind farm, we can find again, wind farm has suddenly tripped at 10 seconds. So let's take a look about this one. If the figure 1 has tripped at 10 seconds, then if the supercapacitor is 9 kilowatt, it's this way, and then drop down. If it increase to be 19 kilowatt, it's increase drop down. But you can see the value, the peak value here is about 0.2, but here is reach about 0.45. What about the VRB? If VRB choose to be the 26 kilowatt, the highest value is lower than the 0.35. But if choose to the 56 kilowatt, the highest value is lower than the 0.8 per unit. So different value, different capacity will affect the performance of our system. So this is number 4, case 4 for our study. So finally, I will draw conclusion for this talk. So this talk, both stability and economic analysis of a DC microgrid (MG), composed of different renewable power generation system, renewable energy system, and the various energy system, phase 2 kilowatt and the megawatt multi-machine system have been discussed. Second, the study DC microgrid composed of wind generator, a fuel cell, a microturbine generator, a vanadium redox flow battery VRB, a supercapacitor bank, a bidirectional DC converter, and a bidirectional DC-AC inverter has been established. The energy storage system based on supercapacitor bank and the VRB is connected to the DC microgrid through bidirectional DC-DC converter, while the multi-machine system connected to the DC microgrid through the bidirectional DC-AC inverter. The feasibility of the study DC microgrid has been evaluated by using IEEE screen expert for economic analysis. So we can, while the method model of the study DC microgrid with the renewable energy power generation system integrated with the energy system have been established. From the small signal stability, you can find the rural side plot for the study 4 system configuration have been performed to examine the stability of the study system under various wind speed. Dynamic and transient response of the study system under different wind speed, various capacity, southern trade wind farm has been performed and evaluated about the smoothness of the stability of the study DC microgrid. So this is my presentation. Thank you for your attention. And now we have following the question and the answers.
Thank you very much, Prof. Lee. Very interesting and informative sharing sessions. I will open the question from the participants. Any questions from the participant, Dr. Kanendra? Okay, I will read the questions from Saleh Omar Abu Bakar, Prof.
Oh, very good question.
Prof,
very good
how
question.
can we manage the load mismatch of the overall hybrid system? Okay, Prof.
Okay, I show you the, because this system has the DC, AC together. So we have to use the method to solve all the differential equation. Make sure the force derivative of the differential equation must be 0. Then using the Newton-Raphson method to solve all the operating conditions to make sure the load and the power generation are balanced. So you can see we have several generations over there, DC link and the generator and even multi-machine system over there. So the Newton-Raphson iteration method is very, very important for us to study the power flow to make sure the power generation and the load between them are balanced. So maybe I'm not sure this answer is maybe fit your question. Okay.
Okay. Thanks you, Prof. Okay, the second question from the same person. What happened to the hybrid system if the wind loss is less than 4
it's a very good question. Okay. Okay. Each wind turbine has a cut-in wind speed. If the wind speed lower than 4 meters per second, then the turbine will not be rotated. We stop up there. So cut-in wind speed is a condition. If the wind speed higher than cut-in, then the blade will be rotated. If lower than the wind speed, than the cut-in wind speed, then the blade will be stopped up there. Okay.
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 Okay, the third question from Hussein Jahangir. Dear Prof. Wang, how robust, primitive and efficient as well as the initial investment, maintenance cost of the combination of SC and VRFC?
Oh, okay. According to our economic analysis, the VRFB may be very expensive and super bank also very expensive. So that's why do we need the economic analysis? Because each engineering is want to establish, you must perform economic analysis. How much money you invested, how many years you can get back your money. So all this one must be performed before the one engineering is established. So remember, maybe in our department, electrical engineering, most of the students did not touch about the economic analysis. But I suggest all my students have to study about economic analysis because each engineering must be perform the economics in advance. If you can get money, you can earn money, then you can go over there to establish your engineering. So that's the initial investment maintenance, very important. Different engineering has different investment, different costs. So remember, I suggest each one has about our engineer must learn about the economic analysis very in advance before your engineer is one to establish. Okay.
In a way that we have to convince our stakeholder that the one or the technique or the technology that we are proposing is feasible in terms of economy. Am I right, Prof?
Yeah. Right.
Okay. It's not only provide the technology, it's also we have to come to aspect of economics so that the stakeholder or the consumer confidence with our technology or our techniques.
Right.
Okay.
Right.
The next questions. Dr. Kanendra, do we have any question? Okay, Prof. Hazli.
Yes. Professor, how are you? Good morning.
Good morning, Prof.
Wow.
Thank you very much for accepting our invitation.
Thank you.
Okay, Prof. I have maybe 2 questions.
Okay, good.
Okay, maybe first question, maybe you would like to explain a little bit what is the advantage of DC microgrid as compared to AC microgrid, so that we can understand better. Yeah, please, Prof.
Okay, DC microgrid may be combine some of the device with DC output, but even the DC microgrid also connected with the AC through the DC AC inverter. But AC microgrid is very popular because most of output power is AC. But remember, most energy storage system is based on DC. So that's why if all the AC generator want to connect it to the DC energy system, the converter must be used. That's why if you choose the DC microgrid to combine all the power generation together, then your energy system may be easily to connect it to the DC link. But if you choose the AC microgrid, then your DC energy system need a bidirectional DC AC inverter. So there may be a big problem about the energy source connected to the AC grid. So DC grid has its advantage more than the AC microgrid. It's my small opinion.
Yeah. I think what you say is right because the configuration also different, and also in terms of technically with the DC microgrid, it's much more easier to control, as you said, because a lot of battery which is based on DC.
Yeah.
Okay. My next question, Prof. What is the rate of change of the wind speed that the system can cater? Because sometimes if the rate of change is very fast, maybe the stability will be lost. So in your study, what is the consideration?
Okay, wind speed, yes, it's very important because I think most of the paper published just use the constant wind speed. But in my laboratory, we use the actual wind speed. So example, my slides show the actual wind speed captured from the wind tower. That's why when we apply the actual wind speed to our system, each model for your system must be very carefully to establish it, because the wind speed, the frequency of the wind speed may be higher than your model. So each model in our star system must be carefully to establish to make sure your time constant or your eigenvalue must be matched with your high speed wind speed input. So in my research for several years, I understand to establish the stability model is very, very important. Each model has the time speed, the time constant and the equation. So the time constant is a very important parameter for each model. But if you apply to the very high speed wind speed, then you want to capture the such high speed wind speed, then your time constant must be a very, very small one. Then you can capture the high speed. So remember, in our model stability in our slides, each model is based on stability. So stability makes sure that they can capture the high speed wind speed when the high speed wind speed is applied to our solar system. So remember, my study is focused on stability. Because if you study the power electronics, much more high speed will be used to simulate the performance of the switching of the converters. So that's why I focus on stability. Stability means that each model is based on stability problem, and the wind speed input, your constant must match or lower than the constant, time constant of the wind speed input. So this is my small opinion. Thank you.
Okay, excellent, Prof. Last question, I guess, because in Taiwan, a lot of wind farm,
Yes.
and as I know that Prof. Wang also involved in some of the projects there. So
Yes.
maybe you can tell us a little bit, how do you relate your research, theoretical research, simulation with the actual implementation or actual study? Okay, that's the last question
Thank you.
from me. Thank you, Prof. Wang.
Okay, thank you. Because in my laboratory, we have several different commercial software to establish the wind farm model. This is the first one. Second one, I ask all my students have to derive differential equation by themselves. So all my students understand how to derive the differential equation for the synchronous generator, wind model, and the converter. Everyone knows about one. But the important one is that in my laboratory, we also have the very important measurement instrumentation. We can bring the actual instrumentation, go to the wind farm to capture the actual three-phase voltage, three-phase current. Then we can obtain the three-phase active power, reactive power, harmonic, and even the voltage transient. All the quantity we can capture. When we capture all the quantity up there, we can try to use the software to simulate the performance of the wind farm. For example, my first wind farm in Taiwan is in the Mailiao wind farm. Second one is the Penghu wind farm. And then we go to the Taichung, Taoyuan, different wind farm to go there to capture all the data together. Then we bring all the data together to a laboratory. Then my student can use data to compare with the simulation result and to modify the parameter for system. Then make sure the simulation result can very close to the actual major data. So this is my laboratory. We study this one.
Okay.
Thank you, Prof.
Thank you, Professor. Thank you.
Okay, Prof. We have another question here. Okay, can you suggest some software for economic analysis of the hybrid energy system?
Okay, the free, I just mentioned the RET screen is developed by Canada. It's free.
Okay.
So you can use one to try to put the data of your country over there. Each country have different data, including the temperature, raining, or something data over there. Then you can obtain very, very good data for your country. Okay, thank you.
All right. Nice. Okay. From Fakrul Razimata, can we use lead acid or lithium ion batteries in place of VRFB?
Oh, this is a very, very good question. Why do I suggest VRB? Do you know? Because VRB is for grid connection. Remember, it's a grid available for the very large scaled flow battery. For the lead acid, you cannot be used for it because the lead acid maybe have about 5 or 7 years. You have to replace the new one. And the lithium battery, lead-ion battery, has the possibility of explosion. So that's why VRB will not have the possibility to explosion. So that's why I choose VRB as the new flow battery in our laboratory. So because in the future, Taiwan has many different offshore wind farms. The flow battery will be connected to the wind farm to compensate the power fluctuation for the wind farm. So currently in my laboratory, we have a 1.5 kilowatt, very small VRB. But commercially, this one will be extended to be a large one. because it can be extended very large one, just series and pair together. So this one in the future will be very important for our grid-connected energy storage system. Thank you.
Okay, we have another question here. Dear Prof, if the wind energy is considered as moderate generation, is that DC microgrid still significant to be applied even only solar energy is available?
Okay, DC microgrid, the important parameter is the DC link voltage. So remember, what's the capacity of your generation? What's the capacity of your solar energy? You must have an idea in your mind. If your capacity is very high, then your DC link voltage must be increased to make sure the current will not be so large. So depend on your capacity of your generation. Your generation is a megawatt, then your DC link voltage must be higher. If your generation is about kilowatt or smaller, then your DC link voltage can be dropped down. So that's why it depends on your capacity of your power generation system. Thank you.
So that means it's still significant provided that it's fulfill the certain condition that you have mentioned. Am I right, Prof?
Because depend on your even only solar energy is available. Actually, the DC microgrid can be applied to any wind and solar. So many one has used solar. Solar is no problem. It's also available.
Understood, Prof. Okay, it seems that another question. Considering the erratic nature of wind speed, even though the hybrid system consisting of different sources, will it be good to invest the wind speed? In this case, you mentioned about Africa, such as in Africa.
Okay, so this is about the techno problem. So actually, before you want to understand this result about the investment, that's why you need to collect all the data from your country. Then substitute all this data in detail to the economic analysis. Then you can obtain the detailed result for your investment. So I remember the IT screen, the software I think is very good for you. It's free. So you can try to collect all the data of your country and try to put the data into the software. Try to evaluate the performance, whether the system can meet the economic analysis. Okay. So the software, to evaluate software is very important for your, before you are engineering. Before any engineering, economic analysis must be performed in advance. Okay.
Okay. Is there any questions?
Different sources means have different power generation. So you can try to put the different sources to the software, IT screen, and try to simulate the result. Then you can understand it's good for your investment or not. Okay.
Okay. Thank you, Prof. Any more questions? All right. Okay, last question. Prof, I would be grateful to tap your experience in the wind energy system because I have an interest in. Okay, no problem, I guess.
Okay, no problem. Thank you so much. Thank you.
Okay.
Thank you.
All right. Is there any questions, Dr. Kanendra? Okay. We are waiting if is there any questions.
No more, Dr. Farid.
Okay, no more. Right. Thank you.
Thank you so much. Thank you.
Thank you so much, Prof. Niwang, for the
Thank you, Prof.
fruitful, very interesting discussion, sharing session with webinar. Prof, you want to say something, Prof?
I just would like to say thank you very much to Prof. Niwang.
Thank you so much.
Next time we can invite you again to share your vast experience. Yeah.
Thank you so
All right.
much.
Thank you. Have a nice day, Prof.
Thank you. Bye-bye.
All right, we are already in the end of the session. So I would like to thanks for the participant who are actively participant in the webinar sessions. And I hope that to see all of you again to the next program. So stay safe and have a pleasant weekend. Okay, bye-bye.
Bye-bye.
Bye, everybody.
Bye-bye, everyone. Thank you so much. Thank you. Bye-bye. Thank you.